Hello, everybody. Today we have Rocío González Díaz, who will be talking to us about introducing persistent entropy, a tool for topologically summarizing data. Thank you, Rocío.
Okay, thank you very much, and thank you to the organizer for inviting me to this great idea of having this periodical seminar and the YouTube channel that is very good to have access to all the public to this kind of content. So first, I would like to I would like to say that this work is done with people from the University of Seville and also people from North Carolina State University and from the University of Camerino. The outline of the talk is the following. First, I will introduce persistent entropy, and we will see some properties, and we will see 3 different applications of persistent entropy. Also, there are many more. And I wanted to put them because they are applications in very different fields. So first of all, let us introduce persistent entropy. To introduce persistent entropy, I need to recall persistent homology. Persistent homology can be seen as a procedure, an algorithm, in which the input is some combinatorial structure, a simplicial complex, or in general a cell complex, and an ordering of the cells of the complex. That is called a filtration. After a procedure in which each time a simplex or a cell is introduced to the filtration, then a topological class is born or die, we can recollect all of this information to obtain the persistent diagram, or equivalently the persistent barcodes. Let's see an example. Consider this complex, simplicial complex, very easy, in which we have a concrete ordering of the cell, that is a filtration, and then when we add a cell, then a topological feature is created or destroyed. When we recollect all the information, that we have the persistent barcode in this example. And we can store this as points in the plane. So this is the persistent diagram. Okay. Now, we thought, when we defined persistent entropy, we thought that the persistent diagram depends on the filtration. So if we had different ordering of the cells in the filtration, we have a very different persistent barcodes. And we wanted to measure this path. So for example, at the beginning, we wanted to find which is the best filtration that reflects better the topology of the simplicial complex we are measuring, for example. And to measure this, we define the persistent entropy. So giving a persistent diagram, the persistent entropy is the Shannon entropy of the probability distribution obtaining from the length of the bars in the barcode, or the difference of the X and Y in the points in the persistent diagram. Some basic properties of the persistent entropy is that the value of the entropy is always positive and is between 0 and the log of the number of bars in the barcodes, and the maximum value of persistent entropy is obtaining when all the bars have the same length. And this is the case. We have an example, very easy, in which we have 4 bars, all of them of the same length, and then the entropy is the log of the number of bars, in this case 4. And in the case we had before, persistent entropy for this filtration, this ordering of the cells is 1.47, and with the other ordering is 2.19. What can we say here? Sorry. So we can say here if the persistent entropy is very high, then the bars have similar lengths. And if the persistent entropy is close to 0, then the bars are or very short or very long. So it's easier to identify the topological feature because as we know, topological features are represented by long bars in the barcode, and noises are represented by short bars. This was the first idea, or why we defined persistent entropy. Also, we in this paper, we didn't call it persistent entropy. The people that called persistent entropy to this formula was the people from the University of Camerino, and they applied in the following situation. So they consider a set of antibodies that is an immune system. They wanted to simulate or to model what happened when an antigen is injected to this immune system, and then there is a reaction between antibodies and antigens, and after a series of reactions, the antigen is injected again. Later, there is another reaction, and finally, there is a steady state. So how to model this using persistent entropy? First, the idea is how to capture the data. So the data is captured in a matrix, and in the matrix, we store the consistent coefficient between any two idiotypes. An idiotype is an antigen or an antibody. So two antibodies can coexist together depending on some affinity, and antigens also. Okay, so at the end of the day, what we have is a matrix of coexistent coefficients at each time t. What we do with this matrix, we can compute the weighted graph at each time t, where the node represents an idiotype, an antigen, or an antibody, and the weight is the coexistent coefficient between these two nodes. Okay. Then, with this weighted graph, we can compute filter simplicial complex using the known technique of click filtration. Okay. The idea is that we order the edges by their weights, and for example, we order the maximal simplices, the clicks of the graph, by the weight of the minimum weight of its edge. So in this case, for example, in which the ordering follows the ordering of the weights of the edges is this one. We first, in the filtration, we first put this triangle, then this second one, the third one, and the fourth one. Okay, so at each time t, we have a filtration, and for each filtration, we compute the persistent diagram, and from then we compute the persistent entropy. So at each time t, we have just a value. With all this value, we recollect in a function. We have a function that evolves along time, and what the author of this paper noticed is that only looking at this function, we can perfectly and very clearly see when the antigen is injected, when the reaction reach the highest level of reactions, when the second antigen is injected here. This is the first one, and this is the second one. When the maximum number of reactions is produced, and when the steady state is reached. So using just persistent entropy, they could summarize all this information in just a function. Okay. Later.
Pause. Can I ask a quick question?
Yes.
This is both for the application and also some of the figures earlier. When you're computing homology in many different degrees, say 0-dimensional, 1-dimensional, are you computing the entropy separately? Do you average them?
Yeah.
How does that work?
So there are different approaches depending on the application. In the one that I show you here, we only use the 0-dimensional persistent homology, but there are other people that use persistent homology in any dimension. And for example, they compute persistent entropy separately, or they weight the persistent entropy in each dimension. They put a weight and then they sum, and there are very different approaches for this. So there is not only one approach.
Thank you.
Okay, in this case, we have another different motivation that consists in how can we differentiate topological feature from noise. Our first idea is that maybe we can use persistent entropy for this task. So the input in this case is a point cloud. And to obtain the persistent entropy, what we do is we compute the deviatory risk filtration. Remember that for computing the deviatory risk filtration, we put a ball centered at each point in the point cloud, and then we enlarge the diameter of the balls. And when two of these balls touch, we add an edge. And then we can, if the three balls touch, then we add a triangle and so on. So we, the balls is getting bigger and bigger until all the points are connected. And we have only just one connected component. So we can compute, for example, in this case, we can compute persistent barcodes of dimension 0 and dimension 1, and we have two different information in each dimension. In this case, for example, we can compute persistent entropy of the two barcodes. We have two different persistent entropy, or we could compute the combining both or whatever. In this application, we compute separately, and the idea is, as I told you before, is that long bars correspond to topological feature and short bars correspond to noise. So how to detect the long bar and the short bars in an automatical way? The idea we had is that, okay, we compute the persistent barcode of the deviatory filtration, and we sort the bars of the barcode in decreasing order. And then we compute the normalized persistent entropy, that is just to compute the persistent entropy divided by the length of the number of bars. We do this just to obtain a value between 0 and 1. And the key idea, we can say, is that for each of the longest bar, we neutralize them in the way that we change their lengths by a length that maximizes the persistent entropy. Okay, and we will see later why. So we compute the normalized persistent entropy each time in the algorithms, and then we have a sequence of persistent entropy, and comparing the persistent entropy as time I with the previous persistent entropy, we can decide if the bar is a topological feature or not. Of course, this measure, I put it among quotes, because it depends on the application. It's sometimes we need to consider more bars as topological feature or less, but studying this measure, we could do this. All the details are in this paper. I'm not going into the details, sorry, because we don't have time, but I wanted to give you the general idea. So in this example, we consider dimension 0, And we compute the Viettori-rich filtration, the persistent diagram, and the entropy value. Okay, this is the persistent diagram, and the entropy value, normalized entropy values is 0.8. Okay, then we neutralize the longest bar, the first bar. For doing this, we change the length of the bar until we reach the maximum possible value if we only change one bar. We do the same with 2 bars, we do the same with 3 bars, and so on. It is true that always, because we always try to reach the highest possible entropy, that this is an increasing sequence. And at the end, I will always have 1, because at the end, I have all the lengths of the bars at the same value. So if we compare what happened with the persistent entropy, the idea, there is a more complicated formula, but the idea is that there is a big difference between these two persistent entropy and a big difference among what between these two persistent entropy and a small difference between these two and so on. Okay. So this is in the paper. This is established by a function, a formula, but it follows this idea. So looking at this sequence, what we can say is that the first two, for example, the first two bars are topological feature, and the rest are noise. And we can see this because we have here only, or we can see clearly everything among what 2 connected components in dimension 0. Okay. Yes. So for doing this, we have normalized the persistent entropy by dividing the entropy value by the log of the number of bars. In other paper made by different people, they define another kind of persistent, normalized persistent entropy. They divide the entropy by the log of the total length of the total sum of lengths of the bars. So in this case, the normalized persistent entropy goes from 0 to log of n divided by log of L. Okay, so why they do this? They do this because they wanted to detect the dynamic state. So they want to analyze time series and to characterize the dynamic state using persistent entropy. So this is the point summary reflected here in this procedure. And a very important point that for us they say is that they cannot easily compare persistent entropy value across different diagrams with different number of points. And this is the key. So at the beginning, if we consider persistent entropy and just it, persistent entropy is not stable. That is, as they say, it is not easily compared persistent entropy if 2 persistent barcodes have very different number of bars. Easy means that it's not stable. So we study the stability of persistent entropy. What we saw in this paper is that persistent entropy is stable if we put some constraint. The constraint is that the number of bars, if we compare 2 persistent barcodes, is similar. So the difference between the two, the difference of number of bars between the 2 persistent barcodes is small. And also, there is a problem with the bars of infinite length. They have to be truncated to a fixed value, all of them, if we want something stable. Stable meaning that a small perturbation in the input data produce a small perturbation in persistent entropy. Okay, so this small perturbation depend on the small perturbation in the input data and in the small difference between the number of bars of persistent barcodes. So, for example, where we can ensure that the procedure is stable. For example, when we work with point clouds and we compute deviatory refiltration, we take the zero-dimensional persistent barcodes, and all points have the same number, all point clouds, sorry, have the same number of points, and the infinity bar is removed. There is only one because we work with zero-dimensional persistent barcodes. If we want to design a procedure using this constraint, we can ensure that this procedure is stable. If we use another higher dimensional persistent barcode and we don't have the same number of bars in barcodes and so on, we should be careful and use the formula that we present in this paper to control what happened with the stability of the procedure we decide. Okay. Okay, so we have stability under some constraint. Scale invariant is always, so if we have two different point clouds, but because one is the reside of the other one, then they have exactly the same entropy, persistent entropy value. And of course, a very important property is that we can reduce the dimensionality to 1. So even if we have a very high dimensional point clouds, at the end we always obtain a number, summarizing the topology of the point clouds. Okay. One bad news is that we can have very different point cloud distribution, but all of them can have the same persistent entropy, like in this case. So we have 4 very different point cloud distribution, and all of them have 4 bars in the barcode with the same length. So the entropy is always the log of the number of bars. So persistent entropy cannot distinguish this distribution of points in this case. What can we do in these cases? So for dealing with these cases, we defined a summary function based on persistent entropy, in which we multiply by, we can say, a weight. We sum at time t, okay, time t, we sum the persistent entropy of the bars that are alive. So we have a function, and you can see in this last row, these summary functions are very different in the 4 cases. This summary function is also stable under some constraint, like the persistent entropy value. Okay, so this is a way to deal with this kind of problem, and there are other ways to deal with them. For example, the persistent curve that were defined by other people, and also depend on the application. So these are the introduction of persistent entropy and the properties. Now let us see some application that we made by our groups, and in a very different field, for example, in emotion recognition. In this experiment, we consider database of videos. The database is a very well-known database of emotion recognition, in which the actor simulate emotion, in concretely 8 different emotions. And what we want is some procedure to automatically recognize the emotion. One very important of this database is that the landmark of the spaces are pre-computed, so we don't have to pre-compute it. We use the landmark of the faces in each frame to compute the Delaunay triangulation. From the Delaunay triangulation in each frame, we connect the corresponding landmark points to obtain a 3D cell complex. Then the filtration are considered following different directions. So we order the cell following different directions. This is to capture all the gestures of the motion, of the small gesture we do when we express an emotion. Then we compute 8 different persistent entropy from the H filtration we consider, and then we have an H-dimensional vector. This is only from the image sequence. And from the video, we do something similar. We consider the audio signal. We take exactly 1,000 points. This is for the sake of stability. We need to consider always the same number of points. And then we use the lower star filtration. We compute the persistent entropy, and we have a one-dimensional vector. So we have an 8-dimensional vector from the image sequence and one-dimensional vector from the audio. So finally, we have a 9-dimensional vector that represents a video of a talking face of a person expressing an emotion. Also, I didn't say that we have always the same number of frames, if maybe 27 or something like that. Everything, the details are here in the paper. So we here also have the same number of points. Okay, so stability is 1 and 3. Then we use this set of 9-dimensional vectors to feed a neural network, to train a neural network. It's a very simple neural network. We only have 3 hidden levels, and the entry is 9-dimensional because we have the input 9-dimensional vector, and the output is 8-dimensional because we want to recognize 8 emotions. So we divided our set in training set and test set, and we train the neural network and test the neural network with the test set, and obtain an accuracy of 95%. The good thing is that it is better than the state of the art and we evaluate it in the same database for fairness comparison. Okay. So this is for this application, and the second application we use a totally very different images, or not sure, and they are images of epithelial tissues. These are 3 kinds of epithelial tissues, and we want to study the topology of and geometry of the distribution of the regions or the cells in these tissues. How can we do this? So here the idea is to compute the centroid of the regions, and we compute the Vittori filtration, the 0-dimensional barcodes, and the persistent entropy. More or less, this part is more or less the same always. So one trick that we have to do here is to make something, because we need to have always the same number of points, as we say, for the sake of stability. How can we do this? Here, this is the digital image obtained from the tissue. Okay, so these connected components are the regions. The 0 means the frontier or the boundary of each region. And then we start from the center of the image, and using a spiral movement, we count the number of connected components until we have the desired number, a fixed number. So with this procedure, we can guarantee that we always have the same number of point cloud, the same number of centroids. Then we can do this with a set. We did this with a set of epithelial, of digital images obtained from epithelial tissues, and looking for the persistent entropy, we obtained that the persistent entropy of this epithelial tissue is very different from these two. Also, persistent entropy cannot differentiate these two tissues alone, but using other more complicated procedures that explain it in this paper, the authors are also able to differentiate these two tissues using persistent entropy and so on. Okay. And one important thing that the authors discovered in this paper, is that persistent entropy is highly correlated with the weights of the minimum spanning tree. So they show that the more homogeneous the weights in the minimum spanning tree are, then the higher the persistent entropy is. So there is a relation. Okay. This is an example. Here we have a high, so the weights of the minimum spanning tree is higher than in this other point cloud distribution, and also the persistent entropy is higher in the first point cloud than in the second one. Okay. And the last application is related with philology. So in this experiment, we consider 3 different poets from the Spanish Golden Age: Góngora, Lope de Vega, and Quevedo. We took a set of poems of the 3 poets, and we wanted to topologically characterize the poems of each of the poets. Okay, so we want to extract topological feature from the poems. How can we do this? First, what we did, and it's very logical, what we first did is to compute, or the procedure we did is to embed the words in a high dimensional space using a word embedding, very known in artificial intelligence. For example, I think we use word2vec. And the key idea of this word embedding is that words that appear close in the text, then they are close in the embedding. So if these 2 points are close here, it's because they represent 2 words that are close in any of the points that we use to feed the neural network. Remember that we used to feed, what we use to feed the neural network are the point, all the points of the 3 poets we consider. So for each poet, we have a lot of point clouds. In this point cloud, we have words of all the points considered from the 3 poets, and then we extract for each of the poets, we extract only the points that appear in the poems of this concrete poet, and we compute the Vietory refiltration. From the Vietory refiltration, again, we compute the stereo persistent diagram, and we do this for the 3 poets. Here, we take the minimum of the number of bars that appear in each of the persistent diagram. This is, again, for the stability purpose. And finally, we compute the persistent entropy, consider the n longest bar in each case. So we did this for each point that we consider, and for example, for Gongora. So we have a set of points, and for each point, we compute its persistent entropy. We have a set of persistent entropy, and we wanted to know if they are this value associated to each point is representative for each of the point, or each of the points, or they are just numbers that they don't have to do with the points. So we apply contrast tests, and we see that yes, there are significant difference between the persistent entropy associated with the points of Góngora, the poems of Góngora, and the poems of Lope de Vega, and all the other combination. So we can say that persistent entropy is a good signature for poems of each of these poets. And what is more is that we know, because the Philology studied a long time, that Góngora belong to a literary style different from the literary style of Lope de Vega and Quevedo. In fact, Góngora belong to culteranismo, and Lope de Vega and Quevedo belong to a different style called conceptismo. Is persistent, I don't know, persistent homology reflect this? And the answer is yes, because if we compute the bottleneck distance between the persistent diagram of points belonging to different points, we obtain that the bottleneck distance between the points of Lope de Vega and Quevedo is very small, the bottleneck distance, compared to the bottleneck distance between Góngora and Lope de Vega, and the bottleneck distance between Góngora and Quevedo. So we can say that Lope de Vega and Quevedo belong to the same literary style, or they are very close, and Góngora belong to one that is different, because the bottleneck distance is higher. So apart from this application, there are many more. For example, I put here some representative one in medicine, that persistent entropy in this case is used for heart rate variability. Also in economy, persistent entropy in this paper is used to analyze the stock markets. Also, there are some papers for studying complex system, time series. Also in medicine, there is another use of persistent entropy to analyze or to distinguish skin disease. Another one in medicine is to detect epileptic seizures. And in biology, there is another one for biomolecular structure characterization. So we can say that persistent entropy can be considered very adaptable to the application and versatile. Summing up, we can say that it is a scale invariant, one-dimensional summarization of persistent diagrams. So the thing is that since it is just a number, it's very easy to use in machine learning. And also it is important that it's stable under some assumptions. So we have to take to be careful. So we have to be careful how to use persistent entropy to have a stable procedure. And finally, persistent entropy alone maybe is not enough, so we have to define more sophisticated summarization based on persistent entropy, like summarized function or persistent curves. And with this, I wanted to say thank you, and I finish my talk. Thank you very much.
Thank you so much. Okay, so before we go to questions, I'm going to ask everybody if you can please unmute yourself and applaud the speaker.
Okay, thank you.
That's our tradition here. Okay, questions. I see some hands raised. Or you can just go ahead and unmute yourself. Any questions for Rocío?
Hi, Rocío.
Oh, go ahead, Hamid.
I'm sorry.
Hamid. Hello, Hamid.
Hi, Rocío. How are you?
Fine, and you?
Good, thank you. In your emotion classification problem that you investigated, what is the nature of the audio?
The audio.
Yeah. So, so you're looking at a video, but
Yeah.
what is the audio content like? I'm just trying to kind of work it out in my mind as to what it is we're actually after.
For the channel, we only use the raw signal. So I think it's the basic signal you can use when you have the audios. I know you can have a lot of information from the audio, but we only use one dimensional signal, the raw signal. I don't know if.
But in terms of information, though, how informative? I'm just trying to sort of assess the the amount of information you're extracting from either the video, from the optical versus the audio.
Yes, no, we don't use a very sophisticated method. We only take the signal, more significant signal that I remember it's called raw signal. So it's one-dimensional signal. We didn't take the all the signal that we could take from the audio. I don't know if this is what you are asking. Only one-dimensional signal. So we sample the signal in 1,000 points. So we have a one-dimensional simplicial complex, only vertices and edges. And from this simplicial complex, we obtain the filtration using low star filtration.
Okay, all right, thank you.
Henry, you had a question?
Yeah, I had a question. So for the video example of measuring emotions, I imagine that you had the same people making multiple emotions.
Yeah.
And I was wondering if you had any conjectures as to why you were measuring the difference between emotion as opposed to the difference between the person. So it seemed like you were tracking the emotion more strongly than the person, which is impressive.
So you are asking if there is a difference between emotion in persons. Also,
you were measuring happiness versus sad versus frustrated instead of, oh, this is all, person A versus person B versus person C, which is pretty cool that it's sort of able to detect the emotion even despite different faces.
Yes, if we want to try to differentiate people using this technique, we will fail. So this technique won't differentiate people because we look for using this filtration in all these directions. We use 8 different directions. We look for very small gesture, capture the very small gesture you use when you express emotion. For example, if you are happy, then your eyebrows go up, and then this is captured because using what direction, or the mouth. Then the mouth is different movements. So the same people can have different movements. So we cannot detect the person. We can detect the emotion because of this. Yeah, we should use another kind of filtration if we want to detect the person. And I don't think it is easy. Maybe you need some geometrical things, no? The size of the eyes, I don't know.
Great, thanks. That's very strong.
I have 2 questions from the chat. The first is from Renata Torkesh. Could you give some intuition about what the persistent homology / entropy is capturing about the text in the third application? I was confused if the distance reflects semantic difference or position in the poem, etc.
Yeah. No, I don't think it's semantic. It's the position of the words. So different poets prefer different words and different ordering of the word in the poems. So the key in the, we use poems and we don't use, for example, books, because for defining the word embedding, we need a length of the window. And if we use poems, the length of the window is very easy. It's the length of the, I don't know how to say, in the poem, the length of the poem. No? And then this is why I think we were successful in this application, because we use poem and because each poet prefers some kind of words and in a specific order, yeah, relative order in the poem.
Okay, we have another question in the chat from Reina Andreeva. Very interesting work. I wanted to ask, in the emotion recognition problem, have you tried to not include the audio data? Could the images be good enough on their own? And how much extra information is the audio adding? Do you have any explanation? Thank you.
Yeah. Yes, it's true that most of the information is in the image part, in image sequence part. So the audio is only half. We could remove maybe, but we think that maybe it could be useful. We didn't test this, but we think it could be useful when sometimes when you cannot differentiate only with images, maybe you can differentiate with the audio. So yeah, this is the answer. We put together because we like this mixture, but in fact, it is true that the more information is given by the image sequence.
I actually have a question myself. So having seen the definition of persistent entropy, imagine, if you have two persistence diagrams that are the same number of points and aligned, you could try persistent cross entropy, persistent KL divergence.
Yeah.
I guess you would need an alignment, you would need to deal with the number of points. Have people thought about this? Do you have any thoughts in that direction?
Yes, I know there is people thinking in relating information theory and TDA. For example, this is something that I want to do with Hamid Krim. So yes, definitely something that we have to do. So to go to other more interesting summarization, not only persistent Shannon entropy is the easiest one, the first one that you think, but we need to explore more. Yeah, I think there are people that are also in this line doing this kind of thing, information theory and TDA. So we have to look for this paper. Yes, but the idea of persistent entropy is that it's so simple. But it's also so versatile that you can use very and you can define very simple, for example, neural network, machine learning to feed. You can feed very easily because it's only one dimensional, it's only one point. Then it's easy to find application using it. So you don't need to do very complicated things to find something.
Interesting. That's very cool. Are there any other questions from the audience for our speaker?
So I have a question. Hi, Rocío. Hola.
Hello.
So coming from or related to this invariant to information theory, so when you look at a diagram and you compare diagram, is there any intuitive way to interpret this number? So perhaps, yes, in information theory, when you look at the persistent entropy, you look at in some sense the uncertainty that you have in the distribution in your variable. And the question comes from, so I am working in an application for persistence entropy. When you look at a time series, I'm working in time series coming from electroencephalograms.
Yeah.
And when you have an epileptic seizure, it's like you have a different behavior of the joint behavior of the sinus, and the entropy really change when you have this kind of different correlation between the different sinus and the different. So is there any kind of easy way to interpret this number in terms of the uncertainty? You look at the bars on the length of the bars in the diagram.
I know that Mateo Rucco worked on this. You know this paper, right? About epileptic. I have here. Okay. Topological classifier for detecting the emergence of epileptic seizure. And I know that he divided the time series in windows, and for each window, he computed the correlation between the time series, and from this, he computed the persistent entropy, but I don't remember the details.
Okay. Oh, I will look at this paper. Okay. Yeah, because it works really well in this kind of sinus where you the behavior, the common behavior of the sinus is really changed.
Yeah.
Okay. Thank you.
Any other questions for our speaker? Okay, so if not, I'll end the recording now. And if there are any other questions, we can take them off recording.
Okay.